Linear regression, simply put, is to fit the best straight line through some data points. We can draw different lines through the plot. Some deviate greatly from the dots, and some seem to fit better. The quality of fit is measured by the residual, the vertical distance between a data point and the line. The goal of linear regression is to minimize the total residuals. When we first learned linear regression, we were told to minimize the sum of squared residuals instead of just the sum because squaring prevents positive and negative residuals from cancelling each other. But this got me thinking, why don't we take the absolute value of the residuals, the fourth power, or any other methods that make the residuals positive? In fact, your econometrics professor probably didn't tell you the entire truth. We use the sum of squared residuals not just to accumulate residuals properly. There is a deeper reason why we do it. Welcome to Luck by Numbers, where luck meets logic. If you're here just for the answer, here you go. When we use the squared residuals as our loss function, the best predictor is the conditional mean of the output y given the input x. Now that you know the answer, here's why. The loss function is the value we try to minimize. Here, y is the actual value and z is our prediction for y. The expected risk of a regression problem is the conditional mean of our loss function given the input x. This measures how far off our prediction is from the actual data on average at point x. The base predictor is the predictor for y that minimizes the expected risk. This is how we define the best predictor in this scenario. Let's see what happens when we choose the squared residual as our loss function. The expected value can be represented by this integral. We want to find the value of z that minimizes this expected risk. To do this, we take the derivative of the expected risk with respect to z. Setting this derivative to 0 gives us the condition for the optimal z. Simplifying the resulting equation, we get the following. Expanding this equation, we split it into two terms. The integral on the left-hand side is 1, as it simply sums up all probabilities. This leaves us with z. The integral on the right-hand side is the definition for the conditional mean of y given x. This shows that the base predictor under the squared residuals loss is the conditional mean of y given x. In other words, minimizing the sum of squared residuals aligns perfectly with predicting the mean outcome for y given the input x. Let's compare this to other loss functions. For example, if we use the absolute value of residuals instead of squaring them, the best predictor wouldn't be the conditional mean. Instead, it would be the conditional median of y given x. But here's the beauty of the sum of squared residuals. Not only does it give us the conditional mean, but it's also mathematically convenient. The squared loss is differentiable, which makes optimization much easier. That's why it's the foundation of many regression techniques, including linear regression. To put simply, when we minimize the sum of squared residuals, the average value of y for a given x is our best guess at any point x. You're watching Luck by Numbers. If you enjoyed this video, please like, subscribe, and share your thoughts below.